the entire domain is just the rotating part, so be that the impeller of a pump.
Okay.
So we're not considering the volute or any stators, anything like that. Then we step up into what's called a multiple reference frame model, where you've got a rotating component, still got the impeller in there, and then you might have a static component as well. So that can be a volute or a stator blade or something like that. So the other two approaches are both steady state. So we're not solving for time, we're just getting an average solution. You can get within, say, 1% of experimental data, particularly in like the center of the map where the pump's quite efficient. You can get within 1% without going into the transient simulations. So for this model, we just started with a pretty basic axial fan. We gave ourselves a few constraints so that we fit within a particular size and an RPM window. And then we sort of parameterized pretty much every angle you can think of. So that's leading edge angles, trailing edge angles, even the angles within the midspan of the blade. We had varying gaps to the shroud, height of the blades. It was a very highly parametric model. So pretty much, if you put silly numbers in, you could create a very, very strange looking surface. It was a very, very flexible model.
With sensitivity analysis, what you really want to do is first cull out any variables which aren't relevant to the process, so that you can simplify the stages further down the line. It also allows you to look at correlations between inputs and outputs. So most people instinctively go inputs, outputs first, and so that if I change this variable, then I see an improvement in performance, and if I change the other way, I see a detriment. You want to identify in your first pass which of your outputs are correlated with each other. So quite often in fans you get, you might be able to increase maximum pressure, but you end up with dropping efficiency due to separation on certain parts of the airfoil. So sensitivity analysis will give you a first pass representation of what those performance trade-offs look like. It's a fancy response surface, but the one defining feature is that it has the ability to self-evaluate its accuracy. So the way it does it is it breaks up your data into groups, and it will curve fit based on a certain group according to fairly normal response surfaces, and then you'll use the last group to evaluate whether the first group's predicted performance accurately. It means you eliminate the idea of overfitting, because like for example in Excel, if you go and predict data, you can turn up the polynomial count to a factor of 20 and you get a perfect fit. If you go and then place another design point on that, it'll be a poor predictor because you've had noise included in the first time. So the meta model is a self-checking response surface. The trick with a multi-objective analysis is to say, when I come to design my final fan, I'm going to balance these 2 or 3 objectives, and I want to know how much I value each of those objectives. So if gaining 1% efficiency is my absolute priority, and I'm prepared to sacrifice 5 pascals of pressure to achieve it, then a multi-objective allows you to see the curves that show you those trade-offs and how they function. It could be that your target application lives in a certain area where it's very easy to make efficiency improvements and very hard to make static pressure improvements. Because we use meta models in OptiStang rather than the actual CFD results, we sacrifice a little bit of precision in order to gain a dramatic improvement in performance. So rather than taking 10 minutes to do a run, it takes less than a second. So we can afford to do 10,000 runs in a very scattergun type process in order to map out very hard to find designs. Usually if you try to map out Pareto fronts, you'll find that it's very easy to find designs in certain clusters, and it's very hard to find them in the gaps between the cluster.
So we can look at the trade-off between two of our output variables. So if we're trying to design a fan that has a good static pressure rise, but also has a good isentropic efficiency at a various flow rate, we can obtain a curve that shows where this sort of best line of performance is, and then you'll start trading off between, say, high pressure gain over here and high isentropic efficiency over here, and you'll have this curve of sort of best case solutions, and then sort of the next step from there is deciding, well, where on this curve do I want to sit? Do I want to be closer to the pressure gain side, or do I want to make a very efficient fan?